function defined as x squared plus 2x when x is less than negative 2, negative x squared minus 2x when negative 2 is less than or equal to x is less than 0, x squared minus 2x when 0 is less than or equal to x is less than 2, and 2x minus 4 when x is greater than or equal to 2. This function is defined on a domain of all real numbers. But before we start evaluating its derivative, we need to check whether it's continuous at its junction points. Continuity is a necessary condition of differentiability. How can I determine whether it is continuous at, say, the first junction point, x equals negative 2? The way I'll do that is I'll determine what the limit of f of x from the left and the right are by substituting negative 2 into this expression and then substituting negative 2 into this expression. So when I substitute negative 2 into x squared plus 2x, I get 0. When I substitute negative 2 into negative x squared minus 2x, I also get 0. The function has a limit of 0 from the left and from the right, and since f of negative 2 is also equal to 0, it follows that f is continuous at that first junction point, negative 2. Then we'll do the same analysis, substituting in 0 both to negative x squared minus 2x and x squared minus 2x, and we see again that f approaches the same value from the left and the right. It's also 0, and therefore f is continuous at 0. And in the third junction point, again, f approaches 0 from both sides, and therefore f is continuous at 2. It's continuous at all three junction points, and the function pieces are all polynomials, which means that f of x is continuous for all real numbers. Now let's compute the derivative, f prime of x. Well, that's also a piecewise function. The first piece is found by differentiating x squared plus 2x, and I get 2x plus 2. Where does 2x plus 2 apply? The same subdomain as x squared plus 2x. X is less than negative 2. Next, I differentiate the next part, and I get negative 2x minus 2, and that applies in the same subdomain. But wait, you say, it's not exactly the same because there's an equal sign here, and I didn't reproduce the equal sign there. Well, I have to leave out that equal sign for the time being. Before I can put that equal sign in, I have to check that the function is differentiable there. I have to check that it's not a corner, that the derivative doesn't discontinuously change. So I'm going to put a little orange dashed line in place to remind myself that I have to check later whether to include that equal sign. The third piece is found from differentiating x squared minus 2x, and again I'm going to put the little dashed orange line, and the fourth piece is f prime of x equals 2, when x is greater than 2, and again I put the little orange dashed line. Now how do I determine whether f is differentiable at those junction points? The answer is I have to check whether differentiating from the left and differentiating from the right give me the same value. In other words, I have to do the same thing that I did with f. I have to determine whether f prime is continuous. So I plug in the junction value negative 2, I plug it into 2x plus 2, and I get a negative 2. I plug it into negative 2x minus 2, I get a positive 2. These are different numbers. That means f prime is discontinuous at the junction point x equals negative 2, which means that f of x is not differentiable at negative 2. We will have a corner in the graph of the curve. Therefore, I want to remove this dashed orange line. Watch carefully, it's going to vanish, and there it goes. Next, I do the same analysis at the junction point 0. So I substitute 0 into negative 2x minus 2, and I substitute 0 into 2x minus 2. I get the same value, so f prime is continuous at 0, and therefore f is differentiable at 0. So that means that this next orange dashed line becomes black. Then I do the same analysis at the last junction point. I substitute 2 into 2x minus 2, and 2. They're the same value, so the function f prime is continuous at 2, and therefore this last little orange dashed line turns black. And now I've found my derivative function. Next thing that I want to do is find the second derivative, and I will do the same thing, differentiating each piece of the first derivative, and deciding whether to include the equal signs. And all the equal signs go away now because the second derivative is discontinuous at all three junction points. Now that I have found all the derivatives, let's go about trying to analyze this curve by looking for its critical points. Now the first critical points we'll look for are the stationary points. That's the place where the first derivative is equal to 0. So we look at our expression for the first derivative, and we see where it's equal to 0. First I'll look at 2x plus 2, and I see it has a 0 at x equals negative 1. Does that mean that's the stationary point? No, because x equals negative 1 is outside of the subdomain where 2x plus 2 applies. So we reject that, and then we go on to the next part. Negative 2x minus 2, does that have a 0? Yes. It has a 0 at x equals negative 1, but now x equals negative 1 is inside the subdomain where negative 2x minus 2 applies, so x equals negative 1 does turn out to be a critical point, and we put it on the list, remembering that it comes from a 0 of negative 2x minus 2. Then we find a 0 of 2x minus 2, that would be x equals 1, that's inside of the corresponding subdomain, so we have another critical point that's a stationary point, and we remind ourselves that this is a 0 of the piece 2x minus 2, and then we look at the last piece and find the zeros of 2. There are no zeros of 2, so that's all the stationary points. But is that all the critical points? No, remember that critical points are stationary points and non-differentiable points. We found all the stationary points, but I still have to find the non-differentiable points. And if you recall, there was a non-differentiable point at x equals negative 2, because f prime discontinuously changed from negative 2 to positive 2. So we include x equals negative 2 on our list of critical points, reminding ourselves that it was a non-differentiable point. Now I have a complete list of critical points, and before I go on and look for the inflection points, I can analyze these critical points using the first derivative test. So x equals negative 1 is a 0 of this decreasing function, negative 2x minus 2. The 0 of this function occurs when the function is changing sign from a positive number to a negative number, and therefore x equals negative 1 will correspond to a maximum of the function f by the first derivative test. Now, 2x minus 2 is an increasing function, so its 0 is a place where it changes sign from negative to positive, and the first derivative test says this is a location of a minimum in f. And x equals negative 2 is a non-differentiable point. Remember that the derivative changed from negative 2 to positive 2, so we have another negative to positive, and that means there is a minimum at x equals negative 2, a minimum of f. Now let's go to the inflection points. The inflection points are places where the second derivative changes sign, and we see, if we look at the very first two expressions for the second derivative, we see that it changes sign at the first junction point of x equals negative 2. Does that mean negative 2 is an inflection point? Careful! Remember, x equals negative 2 was a non-differentiable point. There's another requirement of inflection points besides the second derivative changing sign. You also have to have a tangent line that exists. So x equals negative 2 is not an inflection point. We have to reject it because there's not an existing tangent line at x equals negative 2. Next place where f prime changes sign is at 0. Changes from negative to positive. So x equals 0 would be an inflection point. Now, does f prime change sign ever again? No. Going from 2 to 0 is not a change of sign, because 2 is a positive number and 0 is neither positive nor negative. A sign change would be from positive to negative or negative to positive. Going from positive to 0 or negative to 0 would not be a sign change. So there's only one inflection point, and that's at x equals 0. And I want you to notice that we have an inflection point where f prime does not equal 0, and we have f prime equal to 0 where there's no inflection point. It's important to understand that the inflection point doesn't automatically happen whenever f prime equals 0. Now that we've analyzed all the critical points and the inflection points, let's look at a graph of the function. We start off with the curve x squared plus 2x. We know that the junction point is at y equals 0, and we know that we're starting out with a concave up curve, and we're going to come to the junction with a derivative of negative 2. There's a concave up curve, it comes down to 0, and the derivative is negative 2. And on the other side of the junction point, we're going to have concave down curve, and the derivative is going to discontinuously jump to positive 2. And it's going to be negative x squared minus 2x. It looks like this. It has a stationary point right in the middle at x equals positive 1. Comes back down to 0, still concave down, and now it's going to change into a concave up curve, and it is differentiable at that point. So x squared minus 2x fits on in a way that makes the tangent line at the origin exist. And doesn't that look like an inflection point? Yeah, just as we predicted, x equals 0 is an inflection point. And then the last part of the curve is a line, and we're going to attach the line in such a way that the derivative at that junction point exists. In other words, the derivative is 2 on both sides. So that's what the graph of f looks like, and just as we predicted, it has 3 critical points. X equals negative 1 is right here, corresponds to a maximum. X equals positive 1 is right here, corresponds to a minimum. And x equals negative 2, the non-differentiable point, corresponds to a minimum. So everything we predicted is seen in the graph of the function. We're brilliant.